Hi, it's Dr. Sherman. I'm going to outline the thermal expansion of solids lab. In this lab, you will investigate how the dimensions of solid materials change with temperature. Specifically, we're going to have a tube of copper metal, going to put it into a steam container and heat it up and measure the expansion. Now this is going to be a video that you're going to watch and take data from. There are some new tools in this video that you may be unfamiliar with. One is going to be a digital thermometer, and you're going to determine the available precision of the digital thermometer using a spec sheet. And the second is a micrometer dial. In Activity 1, you're going to measure the temperature from a digital thermometer and use a spec sheet to determine the allowed precision of the measurement. You will also read the change in length from a micrometer dial. You will calculate the coefficient of linear expansion from the initial and final measurements of temperature and length. So as I mentioned, we're going to heat up a metal rod and measure the expansion due to an increase in thermal energy as measured by the temperature of the rod. So the rod's going to expand as the temperature goes up and contract in the same manner as the temperature goes down. This follows a linear equation. Change in length equals the initial length times the coefficient of linear expansion times the change in final to initial temperature. So for Activity 1, you're going to get values for initial temperature, final temperature. Oops, I had a typo. Initial length and change in length, and we're going to calculate the coefficient of linear expansion. For the Extech thermometer, which you'll be using through the video to measure the temperature, it is a digital device, but just because it's a digital device does not mean it measures more precisely than an analog device or a device where you have to estimate the error of the measurement itself. So for this particular thermometer, it's actually less accurate than the display actually shows. So here's how you find the precision allowed by a digital device. First thing you want to do is take the measurement and see what the display shows. I'm taking a measurement of roughly boiling water, so I'm reading 96.7 degrees Celsius. Based on that value, I'm going to go to the accuracy specifications of the device, which are provided to you in the introduction of the lab. My temperature falls in the range of 0 to 1,000 degrees Celsius. Therefore, the precision, here indicated by accuracy, but it's being used to designate the uncertainty of the value. So my precision is can be calculated based on this particular equation. So my equation is 0.3% of the reading plus 1 degree Celsius. So 0.3 degree of my reading, and my reading's just shy of 100 degrees Celsius, plus 1 degree Celsius gives me 1.29 degrees Celsius. Now remember, I can only report uncertainty to one digit, so I need to round this value. If I round it down to 1 degree Celsius, then I'm estimating my error to be actually lower than it is. So I always need to round up to the next significant figure. So I'm going to round up to one digit. Rounding up makes that 2 degrees Celsius. So what I'm finding is that I can read 96.7, but I'm only confident that my reading is 97 degrees Celsius plus or minus 2 degrees Celsius. Now, as you can see, I'm providing you with a video. You can clearly see the thermometer and the display we're going to use to read the values of temperature. This is the micrometer dial. You should be able to see that as well. However, you may need to zoom in on the video itself. The video includes an overview of the experiment. I will start the micrometer at 0, and the initial temperature will be shown. May not necessarily be this temperature shown on the preview of the video, but you will be able to read the initial temperature when the experiment starts. I'm then going to connect the apparatus to a steam pot. The micrometer and the thermometer will be shown while the device is heating up through its connection to the steam. You'll be able to read the max temperature and the total change in distance, change in length of the metal rod itself. You will have a separate video which shows the apparatus cooling down. This will be later in the lab for activity 2. The video shows a micrometer dial being used to measure the total change in length of the tube as it is heating up and cooling down. A micrometer dial is used to measure very small changes in distance. The least count, remember that's the distance between two tick marks. The least count is 0.01 millimeters, and there's 100 increments in the full circle. Because the least count is 0.01 millimeters, and I'm fairly confident you can estimate the needle position to the nearest half a division, so you could estimate between two tick marks, separate it into 2 halves. That will give you an estimated error of 0.005 millimeters. As an example, you see that the micrometer dial is pointing, there's 60, there's 61, there's 62, and I'm halfway between 62 and 63, so I'm reading 0.625 millimeters plus or minus 0.005 millimeters. A piece of information that might easily be missed if you don't read all of the instructions is the initial length of the rod. I measured the initial length for you and have provided it in the lab as 0.348 meters plus or minus 0.005 meters. In the second activity, you're going to graphically determine the coefficient of linear expansion by collecting measurements during the cool down phase of the experiment and graphing the data. Now, a graphical determination of the linear expansion should be a more accurate representation of the linear expansion because the experiment is performed over a greater range of data. In order to use a graphical representation of the linear expansion coefficient, you first need to compare your equation to the equation of a line. Now you have to consider what variables you can change in the experiment and what variables you will measure in response to that change. So definitely we are applying steam to the device or letting it cool down. So the thing that we are allowed to change is the temperature. So we'll plot that on the x-axis because it's our independent variable. We are measuring the change in length using the micrometer dial. This makes the change in length the dependent variable and is plotted on the y-axis. Rearranging our linear expansion coefficient equation to match the equation of a line, y equals mx plus b, we see that the thing that we are measuring in response, our dependent variable, is delta L. Our independent variable is change in temperature. And that means our slope is going to be the initial length times alpha. In this particular experiment, our y-intercept should be 0. Similar to the previous video, there is a separate video for the cool down of the experiment. In this video, it will show the max temperature, the disconnection from steam, and the micrometer dial and thermometer as the metal cools down. Now this video is significantly longer than the first video. There are some questions that you need to answer to kind of establish the overall idea of the experiment and how you're going to take data. I do recommend that you watch a portion of this video either on fast speed or just watch a portion of it to determine the basic construct of how you want to set up your experiment. You will watch the video a second time when you actually need to take data. So you're going to graph delta L on the y-axis and change in temperature on the x-axis, and you will find the coefficient of linear expansion from this graph. For your discussion questions, you're going to talk about errors and uncertainties associated with reading the micrometer dial. And I also want you to address if your data was fairly linear across all data points, or if you think the experimental value for the slope would be more accurate if you eliminated any of your data points. For example, I found that at very high temperatures, my measurements did not match my slope very well, and I recommended that you start at a fairly low temperature of around 80 degrees Fahrenheit. I hope you enjoy this lab, and let me know if you have any questions. Thank you.